So let's finish up our discussion of the cardiovascular system with some discussion of the blood. The blood is our last component to the cardiovascular system, and it has a very important job of serving as the delivery mechanism for all of the different components to our cardiovascular system. Now, in addition to that, it has a variety of additional functions, such as blood clotting and specifically transportation of oxygen, nutrients, etc. So first, let's talk about the basic components of blood. Blood serves as your delivery mechanism, and the reason why we need a delivery mechanism is most of our bodily fluids, the bodily fluids that are responsible for supplying our cells, are not mobile. So in order to replenish those fluids, we need to have a delivery system. Now, of course, we are who we are because of our cellular components. So when we look, we see that we have our cell and its nucleus. Surrounding our cell, we have our interstitial fluid. Okay? And then next to our interstitial fluid, we have our blood with our blood plasma. Now, the cells get everything they need to and from the interstitial fluid. So if the cell needs oxygen, it takes it in from the interstitial fluid, and if it needs to get rid of waste, it puts it in the interstitial fluid. But that interstitial fluid is not able to get up and move around whenever it needs to. So if it needs more oxygen, it can't just go to the lungs. If it needs to get rid of waste, it can't just go to the kidneys. So how does the interstitial fluid then get rid of or replenish? And it does that, of course, via the plasma and the blood, because the blood does have the ability to go to the lungs to get more oxygen when necessary. It does have the ability to go to the kidneys to get rid of waste. So your blood becomes the delivery mechanism that replenishes your interstitial fluid, and your interstitial fluid then becomes the fluid that replenishes your cells. Now, in addition to transporting the obvious oxygen and nutrients, we also see that the blood is responsible for delivering different regulatory substances throughout the body, such as hormones. Finally, in addition to delivering these substances that are required for daily use, the blood also becomes important in maintaining the balance of a lot of the different electrolytes and ions and solutes that are necessary for our body to function normally. Finally, whenever our body produces waste, the blood is responsible for removing that and getting rid of it either via the lungs or the kidneys. Now, the blood functions in three main processes. We have transportation, regulation, and protection from disease and blood loss. We just kind of talked about transportation as being oxygen delivery, carbon dioxide transport, waste products, glucose. All of these things are transitory functions of the blood. We also have the transport functions in terms of, excuse me, in terms of your hormones as well. All of that transportation occurs via the blood. Anything that needs to get from point A to point B is going to get there thanks to the blood and the circulatory system. Now, your blood also has a variety of regulatory functions. Regulatory functions for the blood include temperature regulation. Your blood, of course, is predominantly made of water, and water has a very high specific heat. Well, what does that mean? Well, it means that we can change the temperature of, we can add a lot of heat to water, but its temperature changes very little. So, with that in mind, when water absorbs the heat being produced by our muscles, it can bring it to our skin and dissipate it without changing temperature too much. Blood also helps us with the regulation of acid-base balance thanks to the presence of the carbonic acid bicarbonate system. So those would be the two primary regulatory functions. We also see that the blood aids in the regulation of a lot of the balance of a lot of our electrolytes and solutes as they're going to distribute those as necessary. Finally, we have protection from disease and blood loss. Disease, of course, through your leukocytes, your white blood cells, and blood loss in terms of platelets and blood clotting. Bringing us to the basic physical characteristics of blood. Blood itself is slightly more viscous than water, and that is typically accounted for by the fact that we've got a lot of teeny tiny cells floating around in that blood. Viscosity, of course, means thicker. Now, blood itself typically has a slightly higher temperature than what we're used to, or than what we think of, and that's again because blood has that very high specific heat. Blood's pH averages around 7.4, but it can vary from 7.35 to 7.45, and that is its complete normal range. Outside of that, we of course are in an imbalanced state, and a variety of mechanisms will come into play in order to fix that. We'll talk about those mechanisms a little later in the respiratory and urinary systems. On average, your blood accounts for about 8% of your body weight, and its volume varies from males to females. Males have a slight bit more of a blood volume, from 5 to 6 liters, whereas the females is 4 to 5. Now, typically, the total blood volume, as well as the number of cells within the blood, or formed elements within the blood, is maintained very strictly within normal homeostatic mechanisms via a variety of negative feedback loops. These negative feedback loops are important, as the number of cells and the total blood volume and viscosity all play a key role, or can all be very problematic if they're abnormal. So we'll talk about that here in a second. So looking at the components of blood, we see that blood itself consists of plasma and formed elements at its simplest. Blood itself is 55% plasma, 45% formed elements on average. Focusing on the formed elements here for a minute, we're going to see the formed elements are split in between 3 types. You have your red blood cells, white blood cells, and platelets, or thrombocytes, leukocytes, and erythrocytes. Now, why are we calling these things formed elements rather than cells? Well, we're doing that because technically these guys aren't all cells. Platelets are definitely not cells. They are actually fragments of a cell that were created when a cell called a megakaryocyte started breaking off pieces of itself containing chemicals that are going to aid in blood clotting. And you could also argue that your erythrocytes are not actual cells as adults, as these guys lose their nucleus once they mature in order to carry more hemoglobin. Now, we're going to talk about those formed elements again here in a second, but first I want to focus on plasma and its components. Plasma is predominantly water, about 91.5% water, with a variety of solutes in it. Now, the primary solutes in blood plasma are going to be plasma proteins. Now, these plasma proteins are so named because they live in the plasma. That's it. They don't do anything else. They don't live anywhere else. They live in the plasma. They don't leave the blood unless they're not needed anymore and they're being recycled. Now, all of your plasma proteins are going to be created by the liver. The liver itself, very important in this function, which is why individuals in liver failure often need plasma transfusions, since their livers no longer have the ability to produce the plasma proteins that are necessary for normal blood functioning. Now, being that your plasma proteins are the primary solute in blood, they are the most important, as we saw in the last chapter, at maintaining our blood osmotic pressure. So our BCOP was entirely due, I shouldn't say entirely, but predominantly due to the concentration of these plasma proteins. Now, these guys, as I said, are confined to the bloodstream. They don't leave unless they are being recycled. Now, of your plasma proteins, we have they are grouped or categorized into 3 types. You have your albumins, globulins, and fibrinogens. Now, of these 3, albumin is by far the most common, and as such, we often credit the maintenance of osmotic pressure as being a function of albumin, since it is the most common. Albumins, as well as globulins, in addition to contributing to this blood-colored osmotic pressure, also serve as our transport proteins. Remember, back in Chapter 18, we talked about the importance of transporters for the movement of lipid-soluble substances. Now, we also see that transport proteins are used to move small elements and compounds that we don't want to lose. The idea here is if we attach it to a plasma protein, then we're not going to lose it every time the blood travels through the kidneys. This is something we see when we want to move iron around. Iron is something that's a very small element and would easily be lost at the kidneys if not attached to something. And since iron is not something we have in high concentrations in our diet, what we do have we want to keep. So we attach iron to a transport protein in order to allow for that. Finally, we have our fibrinogen. Fibrinogen, as the name implies, is used to make fibers, which are important in blood clotting. Blood clotting is essential to prevention of blood loss, and it involves the insoluble protein called fibrin. Now, remember what we said. Every time you see that -gen on the end of things, that's representing the fact that this is a precursor molecule. Well, fibrinogen is a precursor to fibrin that is soluble. You might think, why would I want a soluble clotting protein? Well, wouldn't that just dissolve and not create a clot? Well, yeah, but here's the thing. If we had to wait for fibrin to be created, we would have to wait too long and we would lose too much blood. So what we end up doing is creating an almost active fibrin in the form of fibrinogen, where we have to make one minor change to convert it into its active fibrin. This means we have plenty of the clotting protein ready and able, so that if needed, all we got to do is turn one little thing, flip one little switch, and we have our active fibrin and we can start clotting our blood. Now, note, about 7% of the blood is your plasma proteins. The rest are going to be your transitory substances. So your remaining solutes are going to be those substances that are transported by the blood, that come and go, which is why I kind of refer to them as transitory. They don't stay in the blood. They don't live there. And that would include things like your electrolytes, your hormones, your gases, nutrients, glucose, amino acids, waste products, all those things that are being delivered throughout the body, but their job isn't to live in the blood. Now, our formed elements, as I mentioned, are so called because they are not all technically cells, which is why we can't just simply say the cells of the blood. Now, the formed elements themselves include your erythrocytes, leukocytes, and thrombocytes. Now, I do expect you to start using your technical terms, as these are terms that you may not be familiar with, you may not be familiar with, although I know you're familiar with the common names. Now, your erythrocytes or red blood cells are responsible for the transportation of oxygen. Leukocytes or white blood cells are going to be the cells that are responsible for your immune response. We'll talk about the 5 different types here shortly. And your thrombocytes or platelets are responsible for blood clotting. Now, one of the most common diagnostic blood tests that you'll exposed to is a hematocrit. And a hematocrit is directly relating back to the ratio of those formed elements to plasma. Now, since the most common formed element is going to be your red blood cells, your erythrocytes, your hematocrit is often referred to as simply the ratio of red blood cells to plasma, since that's the most important diagnostic evidence that you can get from your hematocrit values. In females, we see the hematocrit is normally from 38 to 46%, and males higher, 40 to 54%. This is one of the reasons why males tend to have that higher endurance factor than females, as this is a normal characteristic. Now, your hematocrit itself, if within its normal range, you're great, but if it's too low, you tend to be suffering from what's referred to as anemia. Anemia is the result of a lower than normal hematocrit, typically due to less less red blood cells. This results in a lack of hemoglobin and a diminished ability for your blood to carry oxygen. This can be due to a variety of things. Either the red blood cells are not being produced properly, your red blood cells are being destroyed too quickly, or probably the most common type of anemia is not having enough iron, because if you don't have enough of the building components to make your red blood cells, then of course you're going to be anemic as well. The flip side of that would be polycythemia. Polycythemia results when you have too many red blood cells, and you might think, well, why is this a problem? The more red blood cells, the more oxygen I can carry. This has got to be a good thing. Problem is, the more as you increase your red blood cell count, you also increase the thickness of the blood, or viscosity of the blood, which makes it harder to pump. Okay, increases your resistance, makes it much harder for that blood to travel through those vessels. It's like, moving a milkshake through a straw versus moving a Coke. This is commonly seen in individuals that experience or participate in what's referred to as blood doping. Blood doping is artificially increasing your hematocrit. It's typically done in two ways. Either you inject previously stored red blood cells into your blood prior to your endurance activity, or you inject synthetic erythropoietin, which hopefully you recall back from your endocrine chapter, that erythropoietin is the hormone that stimulates red blood cell production. This is dangerous, as I mentioned, because it's going to increase the viscosity of the blood. It causes the heart to work a lot harder, and often causes blood not to flow very well, and can result in strokes. It can result in hypoxia of tissues where the blood is too thick to travel, and it also can result in heart attacks if it's making the heart work too hard. So this is all very dangerous, which is why it was banned by the Olympic and most professional athletic associations. Problem is, it's very difficult to prove, as you kind of demonstrated, or as was kind of demonstrated with the whole Lance Armstrong debacle, where they continually suspected and accused him of blood doping, but there's no proof, because how do you prove it? There's no drug you can test for. I mean, sure, you can find erythropoietin in the blood, but you can just say that was there because I've been training up in the mountains. So very difficult to prove. So let's have a little bit of questions. See where we're at. So which of the following is not true of blood in its transporting role? And remember, pause if you need to. So, carrying nutrients to cells from the gastrointestinal tract, carrying oxygen from cells in the lungs, transporting hormones from glands to other parts of the body, carrying waste products for elimination, or all of these. Well, hopefully you have chosen B. Not true. Carrying oxygen from cells to the lungs. Well, do we need to bring oxygen to the lungs? Hopefully you're saying no. We need to take the oxygen away from your lungs and bring it to the tissues. So that's what makes B false. Next question. Again, pause if you need to go over your question and think about your answer. Most numerous plasma proteins important in regulating osmotic pressure acts as a transport protein. Well, of all of these, the only one that fits that description is albumin, which is the most numerous, and since it's the most numerous, its concentration is most important in regulating blood osmotic pressure, and of course it acts as a transporter. Finally, blood consists of 45% plasma, 55% formed elements. True or false? Hopefully you are saying false. We would need to switch those numbers. It's 55% plasma, 45% formed elements. So, formation of your formed elements is one of our examples of stem cells in adults. Formed elements, whether you're a leukocyte, erythrocyte, or platelet, thrombocyte, all originate from one single stem cell referred to as a pluripotent stem cell. Now, depending on the formed element, their production varies. Some formed elements die within hours. Some of them last days or weeks. Red blood cells, for example, last about 120 days. In the embryo, all formed element production, the formed element production is distributed throughout your body, starting first in your yolk sac, moving on to your liver, spleen, thymus, and lymph nodes. And then once your skeleton has actually formed towards the end of fetal development, it moves exclusively to your red bone marrow. Once you're an adult, the formation of your red blood cells, white blood cells, platelets, the formation of all of your formed elements occurs only in red bone marrow. So here you have your hematopoiesis. And here we have that pluripotent stem cell. That pluripotent stem cell is going to continually be undergoing cell division, not only to replicate itself, but also to start the process of producing and replacing your formed elements. From the pluripotent stem cell, we then create either a myeloid stem cell or a lymphoid stem cell. Lymphoid stem cells are responsible for exclusively producing your lymphocytes. Lymphoid stem cells, when stimulated by appropriate signals, will develop into, hold on, sorry about that, folks, I had a knock at my door. So your lymphoid stem cells, depending on your chemical signals and what is necessary to be, that is needed in the current immune situation, your lymphoid stem cells are then going to develop into either your T lymphocyte, B lymphocyte, or NK lymphocyte. First, they form a blast cell, which you remember is your precursor cell, eventually maturing into the adult form. The rest of your formed elements, the remaining 6, all originate from your myeloid stem cell line. Your myeloid stem cell line eventually forms either your prourethroblast, megakaryoblast, eosinophilic myeloblast, basophilic myeloblast, your myeloblast, or monoblast. These will all eventually mature into their adult forms accordingly. Now, the question is, when do we know to create these? Well, we know to create these when we experience signals from our hemopoietic growth factors. Now, your hemopoietic growth factors regulate the differentiation and proliferation of your different formed elements. So with this, you see that the 3 primary hemopoietic growth factors are going to be erythropoietin, thrombopoietin, and cytokines. Erythropoietin, as you learned, stimulates the formation of your red blood cells. Thrombopoietin stimulates the formation of your platelets. And then you have a variety of different cytokines that stimulate the formation of white blood cells accordingly. What ends up happening is you have different cytokines that are released for different immune infections, and because each of your 5 lymphocytes targets different different infections, or are better adept at fighting different infections. So with that in mind, your cytokines will stimulate that development accordingly. So let's take a closer look at our erythrocytes. Erythrocytes are your red blood cells. They are the oxygen-carrying component to your blood. Erythrocytes as adults are jam-packed with the protein hemoglobin. Hemoglobin is a cellular component to your red blood cells which binds oxygen primarily. It also secondarily binds carbon dioxide and helps with the distribution of nitric oxide, which is a potent vasodilator. As far as our visual characteristics, your mature erythrocyte is typically a biconcave disc about 8 microns in diameter. This biconcave nature offers an increased surface area to volume ratio, which is very important for increasing the efficiency of diffusion, since oxygen and carbon dioxide are constantly diffusing in and out of this cell, among other things. The biconcave also increases the flexibility of this cell in order to allow it to fit through those very narrow capillaries. And remember, as adults, erythrocytes no longer have a nucleus, and they've also gotten rid of the majority of their organelles. This allows for the cell to carry more hemoglobin, but it also has a side effect of not being able to repair itself if it becomes damaged. That's why erythrocytes only last about 120 days. Now, on average, your normal red blood cell count is about 5.4 million red blood cells per drop for males and 4.8 million red blood cells per drop for females. We are constantly creating new red blood cells because we are also constantly losing and recycling red blood cells. And ideally, for a normal individual that hasn't experienced any type of homeostatic imbalance, the rate of replacement is equal to the rate of production. This is what allows our hematocrit and our red blood cell count to remain relatively stable. As I mentioned, the primary component to red blood cells is hemoglobin, and it's also the component that allows hemoglobin to function properly. Now, it has two primary components. You have the globin protein, which is made up of amino acids. And these amino acids, in addition to supporting the heme pigment component, are also where the CO2 binds, as we will see later in chapter 23. At the center of each one of these four globin proteins, as you can see, two beta chains and two alpha chains, we find a heme pigment. And at the center of this heme pigment, we find our iron. This iron molecule is very important because this is where the oxygen binds. Excuse me. Now remember, this being predominantly a protein, notice how it's folded up. This folding of all of the alpha and beta chains is extremely important to the hemoglobin's functionality. In fact, when hemoglobin loses its shape or has its shape changed slightly, what we see happening is its ability to transport oxygen is affected. So we really want hemoglobin to maintain its shape as best it can. Now, as I mentioned, the primary function of your red blood cell and your hemoglobin is to transport oxygen. Being that each hemoglobin molecule has four heme pigments, and at the center of each of those four heme pigments is four iron molecules, what we see is that each hemoglobin can carry four oxygens. Now, your hemoglobin is responsible for transporting over 98% of the oxygen in the blood. It's also responsible for transporting about 20 to 23% of your carbon dioxide. But remember, that function is linked to an amino acid, not the iron, because we don't want carbon dioxide and oxygen competing for the same spot. Hemoglobin also is known to bind nitric oxide and supernitric oxide. You may or may not know, but nitric oxide is a gas that's produced by your endothelial cells. This gas is important in vasodilation. So what we see is that hemoglobin becomes an important mediator in vasodilation in order to regulate the amount of nitric oxide available, and as a result, the amount of vasodilation that will occur. Bringing us to our red blood cell life cycle. Red blood cells, being that they don't have a nucleus, as I mentioned, aren't going to live forever. Being that they don't live forever, they are going to have to be removed when they start getting worn out, which typically occurs about every 120 days. So at your liver and spleen, sometimes your red bone marrow, but mainly your liver and spleen, first thing we do is we remove the worn out red blood cells from general circulation. We extract the hemoglobin and we start recycling it, because honestly, hemoglobin has a lot of important components and we're going to need to recreate it, so why not reuse those components? So the first thing we do is separate the globin from the heme. Well, if you remember, the globin was simply a protein, so all we need to do is break apart that protein into its individual amino acids and reuse them. Now, those amino acids may get reused to make more hemoglobin, or they could end up in your muscles to make actin, or they could end up in your hypothalamus to produce antidiuretic, or in your pancreas to produce insulin. So that's the first thing we do. The next thing we do is we focus on that heme where we break off that iron. That iron is extremely important, and it's something we may not have a readily available supply of. So if we got it, we want to keep it. Now, we have two options with that iron. First, if we have enough already, then we're going to take that iron and store it away, and we're going to store it away in your liver. But we don't store iron as just iron. We have to attach it to something, and we attach it to the storage protein transferrin. Now, this is very important because iron is known to be a growth factor for certain bacteria. So we don't want it just sitting around stockpiling, because there might be a microorganism that could take advantage of that and cause an infection. But if we attach it to transferrin, those microorganisms that are iron dependent can't make use of them. Now, if we need that iron right away the transferrin is not the storage molecule, sorry, the ferritin is the storage molecule. I apologize. Again, ferritin is the storage molecule. If that iron is needed back at the blood for growth, we need to transport it there. Problem is, again, we don't want iron free floating in the blood because it'll either be available to bacteria for an infection or it'll be lost in your kidneys when you create your urine. So again, we transport it attached to our transport protein, transferrin. This transports it back to our red bone marrow where it'll then be used in order to recreate our hemoglobin for our new red blood cells. Well, that leaves what's left over is the heme minus the iron. And the heme minus the iron gets converted to biliverdin and eventually bilirubin. And bilirubin is the primary component in the liver secretions of bile. Bile is secreted by the liver into the small intestines in order to aid in fat digestion. Bile and all of its components are important fat emulsifiers. These fat emulsifiers help break those big fat droplets up into little fat droplets up so you can further digest them and absorb them. Once your bile hits the small intestine, though, bacteria and enzymes in your small intestine break it down further, either ending up as stercobilin, which is being excreted in your feces, or getting absorbed into the blood and turning into urobilin and being excreted in your urine. But remember, heme was a pigment. And if heme is a pigment, then all of its byproducts are also probably pigments. So what do you think urobilin's pigment color is? Well, hey, it happens to be yellow. And what do you think stercobilin's color is? Well, hopefully you're thinking brown. So now we've solved the mystery as to why your urine is yellow and your poo is brown. It attains those colors as a side effect of the breakdown of the heme pigment in hemoglobin. Finally, let's talk a little bit about when we produce our red blood cells. Red blood cell production is specifically referred to as erythropoiesis. Under normal circumstances, erythropoiesis occurs when at the same rate at which the red blood cells are removed from circulation. But we can adjust it up or down as necessary. And this occurs whenever your tissues are experiencing what's referred to as hypoxia. Hypoxia is a lack of oxygen. Now, this can result from a variety of things, but most importantly, it typically results anytime you go up in altitude. Because as you go up a mountain, the concentration or availability of oxygen decreases. So what does this mean? Well, if you go up to Denver for a couple of weeks, you're going to experience tissue hypoxia, and your body's going to respond and your kidneys specifically are going to respond by releasing erythropoietin. Erythropoietin travels to your red bone marrow where it does two things. First, it speeds up the formation of proerythroblasts, so it makes more proerythroblasts. But here's the thing, we don't need more proerythroblasts. What we need is more proerythrocytes. So in addition to making more proerythroblasts, we also speed up the maturation of those proerythroblasts into mature erythrocytes. So as we make more proerythroblasts and speed up their formation, speed up their maturation into adult mature erythrocytes, we end up having more red blood cells in the blood and a higher oxygen carrying capacity. So what ends up happening is since your blood now can carry more oxygen, it doesn't matter that less is available since we have more guys carrying it. This is why when you see a lot of Olympic training facilities, typically training facilities that are used for endurance activities, they're almost always found up on the sides of mountains. The reason being is we want to stimulate this hypoxic situation for the muscles in the body so that we can naturally increase the number of red blood cells. This is kind of like normal or natural blood doping. But the key here in this scenario is your body ever going to normally increase its erythrocyte count beyond normal, beyond healthy levels? No. This is why normal or natural blood doping by training at altitude is okay, because your body's not going to take you into dangerous areas, dangerous levels. Whereas artificial, you could exceed your body's normal levels and have the resulting side effects. So let's see what we got here with some do you get it questions. Again, pause if you need to, and think about your questions before I give you the answer. So, hemoglobin's primary job is the transportation of carbon dioxide, and its secondary job is the transportation of oxygen. True or false? Well, hopefully you are saying false. It is, again, reversed. Its primary job is O2 transport, secondary job, carbon dioxide transport. The red blood cell numbers about 5.5 million per microliter in an adult male, is convex in the middle, are also called leukocytes, contain the nitrogen-carrying protein hemoglobin, are multinucleated cells. Well, of all of these, which one is the only one that sounds right? Well, hopefully you are saying A, number about 5.5 million. They are, of course, concave, okay, are also called erythrocytes, okay, contain the oxygen-carrying pigment, and are anucleate, meaning they lack a nucleus. Next question, again, pause if necessary. Which statement does not describe a component of the red blood cell life cycle? Ruptured red blood cells are removed by macrophages in the spleen and liver. Biliverdin is the protein that stores iron. Iron is ultimately converted to biliverdin, which ends up in the liver. The transport of iron in the blood the transporter of iron in the blood is transferrin, and urobilinogen is eliminated in feces in the form of stercobilin. So which of these does not describe a component of the red blood cell life cycle? Well, hopefully you are thinking B. It is, of course, heme with the iron. That is the case here. So oxygen binds to the blank on hemoglobin. Well, I just kind of gave this one away, so hopefully it's an easy one, and you are automatically jumping to B, the iron. Now, many of you might be thinking, but the heme pigment, doesn't it bind to the heme pigment? Well, remember, you need to choose the best answer. And in this case, the best answer as to where it actually binds, well, at the center of the heme pigment is your iron. So if iron wasn't an option, then yes, the heme pigment would be correct. But since iron is an option, then iron is a much better choice for this answer than the heme pigment. When hemoglobin gets recycled, what happens to the globin protein? It gets broken down into individual amino acids, which are recycled. It gets stored away as ferritin or transferred back to the bone marrow via transferrin, or it is broken down and excreted via bilirubin in the liver. Well, might be confused because all three of these are correct as far as components of hemoglobin, but which of the following applies to the globin portion? Well, hopefully you recall the globin portion is the protein portion, so when we break that down, we chew it up into its individual amino acids and then recycle them. Okay, so we are going to stop there for this first lecture, and we'll pick it back up with leukocytes, which are predominantly independent study. We'll talk about a few things with Part B.